Alright, this video is a continuation of the example I was working on the prior video. I was decomposing a vector into components, and we had found out that W1, which is equal to the projection of U onto V, and we had found out that that was equal to the vector 6, 5, 2, 5. And so we had completed the first, that's supposed to be a comma here, so let me just scribble that and put a comma. All right, and now the second part of the problem we were trying to work was we wanted to write U, and remember that U is defined as the W1 and the W2 that we had drawn in the picture. We wanted to write U as the sum of two orthogonal vectors. Well, if you look, we've already got W1 right here. So U is going to be equal to 6/5, 2/5, comma 2/5. And we need to add in another vector. So I need to fill this in with W2. And how do I find it? Well, it's not too hard to find it. Let's go over here and down here a little bit, and let's remember that in that definition of vector components, W2 was defined as the vector U minus W1, because we know what vector U is. That was given in the problem. It was 3, -5. And so what I need to do now is just subtract this vector W1, and remember this is W1, we just used it here, and we need it in this equation too. So if I want to break it into components, I need to subtract, write it as the sum of the two components. So I'm going to express this thing, this W2 part, and then I'm going to go, well, let's just do that, and I'll explain what I'm going to do with it next, because that gets too confusing. All right, so I need a common denominator, so I'm going to rewrite that first vector with the denominator of 5. 3 times 5 over 5 would be 15 over 5. And -5 times 5 over 5 would be -25 over 5. And I need to subtract 6 over 5 and 2 over 5. Okay, I'm going to run out of room, so I'm going to do this verbally. Okay, so I'll kind of highlight so you can see what I'm doing. 15 over 5 minus 6 over 5 would be 9 over 5 for the X part, right? For the Y part, I'll use red, -25 over 5 minus 2 more 5 over 5s would be -27 over 5. So that's what W2 is. Now remember, I needed to find W2 so I could finish writing the vector U in terms of the sum of its two orthogonal vectors, W1 and W2. So W2 needs to go up here, 9 over 5, and -27 over 5. So now I need to complete the process. Let me draw a line across here so I can, remember this was my side work down here at the bottom. And now I'm going to come back up here and I'm going to finish writing U in terms of the sum of its two orthogonal vectors. So remember, I'm going to add the X parts together, 6 over 5 plus 9 over 5. That's going to equal, I'll go ahead and do that addition. 6 over 5 plus 9 over 5 is 15 over 5, which is just 3. Okay. And then now let's do the Y part. Let me just pick a different color so that we can follow what's going on. I'm going to put 2 over 5 plus -27 over 5. And that's going to be -25 over 5, and that's a -5, which is what we started out with. So probably they would want us to write this, but what we're doing is we're writing it like this, and then we're showing that it is equal to what they told us it was in the first place. This kind of is, you know, it's checking your work when you add those two vectors together, because yes, they do add up to what the original vector was. So anyway, I had to include that on this video because I never can make a video that goes over 15 minutes or can't upload it to YouTube. So anyway, I had to do this on this video. We'll continue with some more examples. We'll do a finding the... Okay, what if we want to, let's say we have a 200-pound cart and it's sitting on a ramp. So let me kind of draw a picture as we go. Here's a ramp, here's a cart. Got a little handle on it, okay? Got two wheels. 200-pound cart sitting on a ramp. Ramp is inclined, I'll just kind of abbreviate here, ramp inclined at 30 degrees. Okay, from the horizontal. So if this is like the horizontal right here, this angle right here is 30-degree angle. And what force is required to keep the cart from rolling down the ramp. Okay, so let's think about this for a minute. We got, what's going on here is we do have a force that's acting on this cart, don't we? It is gravity, and it's going to be going down like this. So it's the force acting on it, and it's gravity. There's also, so that force of gravity is equal to, I can make this vector here, and I know that if I've kind of drawn this right here, the way it is, that force due to gravity is 200 pounds downward, okay? So I could represent that. That's down. Up and down is like the j or the y part of a vector. So I would write that, if I'm thinking of writing in terms of something I plus something j, I could write this as 200j, and since it's going downward for gravity, it's a negative 200j. Now, to find the force required to keep the cart from rolling down the ramp, we need to project this vector f onto a vector that's parallel to the original vector. Remember, that's called v. And v, if you think about the force due to gravity, the vector v, if I want to keep it in place, I want to keep it right there, okay? So v would be this blue vector here that I'm drawing. Now there's also another vector here. I should draw it in a different color just so we can easily tell what's going on. There's another vector I'll draw in green here. I'm going to call that W1. It's going the other way because since gravity's pulling down on it, it's trying to roll backwards down the hill because it's on an incline, and that force is going to keep it rolling down. You know, the force is wanting to go down the hill, right? Now, W1 in this case is going to be that green vector because that's the projection of the force F onto V. Okay, V is direction of the regular force. So if you think about it, if you were to using my sunshine analogy, because it helps me a whole lot. If I had the sun down here and I'm projecting this force, if the force could be represented as a board and the sun shining on it, it would land right there, right up there where the cart is, okay? So how can I write that? Well, vector V, I'm going to try to color code this a little bit to see if it helps. I'm going to come up here. Vector V, if I want to represent it, it has some, it's acting on a 30-degree angle. So if you think about it, we can represent that as cosine 30 degrees. That'd be the x component of it. And the y component of it, the j component of it, would be the sine 30 degrees, okay, of j. And so the cosine of 30 degrees is square root of 3 over 2. And the sine of 30 degrees is a half, so I'll just put a half j. That's my vector v. So now if you remember, we have a formula, and I'll write it in black down here. The projection of F onto V would be the force that we're looking for here to keep the thing from rolling back. So that's W1 is the projection of F onto V. The little letter is what you're projecting onto. And that's equal to, that's W1 is equal to that, and it's the dot product of the two vectors, and we've got a force vector, and we've got a vector v here that we've represented. Remember the force, this is the force vector right here. I'll put is equal to F. Here's the other vector. These are the two vectors we're working with. We need their dot product. We need the magnitude of the v squared. And we take that and we multiply it by vector v. And we've got vector v up here. So what is the dot product of F dot v? It would be square root of 3 over 2 times 0. Okay, so remember, we take the two x-type components, and remember, there's a 0i that's understood here, because this is just F is just a downward vector, so it has no horizontal part to it. Okay, so remember, I multiply the two x parts, so square root of 3 over 2 times 0 is 0, so there's not going to be anything there. And then if I multiply the j's, let me circle what I'm looking at so you can follow. The coefficients of the j is a half times negative 200. That's going to be a negative 100. Okay, so if I want to write that f dot v is negative 100, so I can put that in on the top of the fraction. And the magnitude of v squared, well, the magnitude of v, going to have to figure that out. Let's see. So we square root the magnitude of v. Let me come up here and write that in green. The magnitude of v is the square root of square root of 3 over 2 squared plus, remember we just take the two parts of it and square them, a half squared. So that's the square root of 3 over 4, so that's the square root of 3/4 plus a half squared is 1/4. 3/4 and a fourth is just 1, so that's the square root of 1, which is 1. So on the bottom, the magnitude of v squared is just going to be 1 squared, so it's just 100, negative 100. And now what I have to multiply, okay, so that's the 1 on the bottom. Okay, so I'm just going to kind of fill in this formula as I go. The thing I need to add in now is the vector v, and the vector v is that square root of 3, it's hard to fit it in there, square root of 3 over 2i plus a half. Let me, I'm going to put it down here because I know you're not going to be able to read it. Negative square, no, not negative, it's just the square root of 3 over 2, comma, a half. All right, so I've got, if I write that down here, it's just negative 100 times all that. So let me just kind of mark all that out. All right, so v is equal to negative 100 square roots of 3 over 2. Well, I could leave it like that. I could multiply it out. I could leave it like I've got it. Sometimes they'll write it this way, negative 100 square roots of 3 over 2 I minus 100 over 2j, and of course we could simplify that into negative 50 square root of 3i. It's hard to read, but if you're listening, you're going to have to listen because, there's nothing I can do about how this records, minus 50j. Okay? And that would be our vector to keep the thing from rolling down the hill.